to do today, we are going to talk about derivatives, but we will talk about derivatives in a multivariable setting. So what do I mean by that? So now, okay, so in the usual setup, you would consider a function, a one-dimensional function, y equals f of x, okay? And you take its derivative, so I remind you that the definition of this derivative, I didn't define the derivative, but this is a definition. And then the key to this, okay, that if you have f of x plus delta x, then you have the formula that it's f of x plus f prime of x delta x. Plus. Now, this is approximate, okay? This is important that it's approximate. And we will talk more about the residual here, during the lecture. Now, what happens in a higher dimensional case? So now, what you want to do, you want to consider, let's say, a function of two variables. So let's say we have that z equals to x squared plus y squared. How this function is going to look like? So the graph of this function is no longer going to be a line like it's here, right? So here the graph we said is a line. Here you have a three-dimensional space, okay? And then for each point here you have a z, which is a height. So here you have some sort of distorted planar surface. Okay? So now the question is, how do you define a derivative? What does it mean to have a derivative here? So I told you that in this case, okay, the derivative is just a tangent line. Okay? So here, the derivative is not going to be the tangent line. The derivative is going to be a plane that will touch this surface in one point, let's say here. And this is going to be called the tangent plane. Now, how do we define a plane? Okay, we define a plane, we have to define a plane with one equation because we have a three-dimensional space. Okay, and then, so let's say we have x1, x2, x3. And how do you define a plane? You can define a plane with one equation. So let's say you have a1, x1 plus a2, x2 plus a3, x3 equals 0. This is going to be the definition of a plane. Okay, this is the equation of a plane. Why is it an equation of the plane? So for example, if I have three-dimensional space. So let's say that a1 equals 1, a2 equals 1, and a3 equals 1. Okay, my equation is going to be x1 plus x2 plus x3 equals 0. So what is it going to be? It is going to be here, if I will fix x1, x2 somewhere here, then x3 is going to be the solution of this equation. So for example, if I have a point x1 equals 1, x2 equals minus 1, and x3 equals 0, this will be a point of this equation. If I have, for example, x1 equals 2, x2 equals minus 3, and x3 equals 1, this is going to belong to this plane. Why? Because 2 plus minus 3 plus 1 equals 0. So what you are going to get here, you are going to get something like this. You are going to have a plane, but this plane is not going to be parallel to any of the x-axis. It's going to be somehow tilted. Okay? So when you want to define a plane here, what you want to do, you want to have some sort of a tilt. Okay? You need basically two directions. You need a vector. You cannot just do it with one number. You have to do it at least with two numbers. Okay? So how do we to generalize, okay, the notion of derivative and how to find the equation for this plane, for this tangent plane, okay? So what you want to do in this case, you want to look on something what we call partial derivatives. How do you define partial derivatives? Well, the definition is very simple. If you have f of xy, say, a function of two variables, this is z, what you want to do, you want to fix y to be a constant, and then you look on this as a function of x, and you can just take the derivative with respect to x. So if you want to have the partial of delta z with respect to x, it is going to be here something of this form. It is going to be f prime of x plus delta x comma y minus f of xy divided by delta x. And here y is kept constant. So in reality, you just move x. So for example, if you have a function of the following form, x squared times y cubed, this is going to be your z. Okay? How do you find the derivatives here? The derivative here you find by keeping y equals constant. So y is a number. You can think about this as finding a derivative of something of this form, x squared times c. What is the derivative of this guy? The derivative of this guy is going to be the derivative of x squared times c prime is going to be, this is a constant, so it goes outside, and then you have here cx. So here you have the derivative of 2cx. Okay? Now, you put the y back, and then the derivative z delta z to delta x is going to be 2x times y cubed. Okay? That's all there is to it. That's all there is to it. Now, what is the derivative with respect to y? Delta z to delta y is going to be what? Here it is going to be the following. It is going to be here, okay, so x squared is the same, y cubed is going to be 3y squared. That's all. Okay? So this is your derivative. This is your derivative. So now, what you're having here, right, you have basically two directions. You have delta x, you have the vector, you have the vector x and y. So you have two directions, and here you can find, and then what you have, you basically, it's a little bit different from what you have here, because in these two directions, one with respect to y to z and one with respect to y, you have two vectors, and we know that the two vectors lie in one plane. So those vectors define a plane. So if you have, for example, in a three-dimensional space, something like this, okay, then you have a plane that goes through those vectors. All right? So because you define two vectors, you define a plane, and then you can define an equation of this tangent plane here. This is a little bit different from what we have here, because here it is defined by one equation, while here we have like two vectors that define the plane. But the idea is the same. Now, why is it useful? Why do we need this derivative? We have the following formula that we had before. Remember that we said that f of x plus delta x equals approximately to f prime of x plus f prime of x times delta x. Here, however, we have the same idea. What we are going to have here, we're going to have the following formula. We're going to have that, let's say we have a function of x, y, and now let's say that we are looking at f of x plus delta x and y plus delta y, and now you're going to say that this is going to be what? This is going to be f of x, y, plus, and now you take the derivative with respect to x, delta x, plus the derivative with respect to y times delta y. Okay? Plus other things. So this is not, of course, this is approximate. So now, how do you use this formula in order to calculate these things? Okay? So let's take an example. So you want to calculate, let's say that we are back to this example, so z equals to x squared times y cubed. Okay, and what you want to do now, you want to look, so now you have that x equals y equals 1. This is going to be 1, so the point 1, 1, 1, you know that it's on this curve. And now what you want to do, you want to approximate the following. You want to approximate the point 1.5, 2. So x equals 1.5, y equals 2. So how do you use this formula to approximate it? Well, it's easy peasy. What is going to be delta x? Delta x is going to be 1.5 minus 1, which is 0.5. Okay, and y, and delta y is going to be 1, right? Because it's 2 minus 1. Okay, and then what you are going to say, you are going to use this formula. So you are going to say that x squared times y cubed at the point 1.52 equals to the following. So the function itself, right, is going to be the function itself is going to be 1, 1. We said that the function itself is going to be 1, 1. So it's 1 plus, and here we're going to have delta f divided by delta x times delta x. So here we're having, well, we said delta f to times delta x. So this is going to be, so we said delta z to delta x is 2x times y cubed. And delta z to delta y, we said that it's going to be 3x squared y squared. Okay, because when you derive by x, you're deriving this, you keep y constant, so you're getting 2x times y cubed. And here, when you derive, you're going to get 3x squared times y squared, because you keep the x squared constant. So then, so when you are evaluating delta f to delta x, this is going to be x equals to 0. Now you're evaluating this at point 1, 1, right? You're evaluating this at point 1, 1, 1. So at the point 1, 1 is going to be 2x, 2 times 1 times 1, which is 2. And here it is going to be 3 times 1 times 1, which is 3. So delta z to delta x at point 1, 1 is going to be 2, and delta z to delta y at point 1, 1 is going to be 3. That's all there is to it. Okay? So now, what are you doing? What are you doing here? Okay, so this is actually easy peasy. So what you are going to say, that now we have 1 now. I'm going to evaluate delta f to delta x. We said that delta f to delta x is 2. So I'm going to have 2 times 0.5, because delta x, we said, is 0.5 plus, and now I'm going to evaluate y. So it's going to be 3 times 1. So it's going to be 1 plus 1 plus 1 plus 1 plus 3, which is going to be 5. So now you approximate the new point at 1.5 and the 2 as 0.5. The correct point, right, is going to be 1 times 1.5 squared times y cubed, which is going to be 2 times cubed. Yeah, so the approximation is not very good, because what's happening here, that those points are relatively far from the point 1, 1. But you kind of getting the idea where it's going to. Okay? So what you want to do, you want to approximate the function at a point which is kind of, which is not the same, which is actually from the initial point. You want to approximate the function. You don't want to compute the function in the new point, because maybe to compute the function in the new point is harder. Okay, so what you want to do here, you're actually taking the original point, you're perturbing it, you are actually using this formula to approximate the new point, to approximate the value of the new point. Okay, now this happened for for function of this form. However, this can be actually generalized. And we are going now to talk about the generalization. So what does it mean to be generalized? Well, you can actually consider more general mappings. Let's say you can consider a mapping from R3 to R2. Say your mapping is going to be something like this, of this form. So you have two functions, f1, x, y, z, equals to x plus y plus z. And then the function f2 xyz is going to be xyz. So then the pair f1, f2 defines a mapping from R3 to R2. Why? Because every point that you have in R3, you can associate that point in R2. Say you have a point x equals 1, y equals 2, and z equals 2. What will be the points that will correspond to the point, in R2? This is going to be 1 plus 2 plus 2, which is going to be 5. Okay, and here you are going to get 1 times 2 times 2, which is going to be 4. So for this point, you approximate it with 2. Is a point that corresponds to z is going to be 5, 4. So you have basically a mapping from a 3-dimensional space into a plane, into 2-dimensional space. Okay? Now, it is very hard to visualize it in, geometrically, because it's like a 5-dimensional space. And we don't have a 5-dimensional space because for each point in R3, you have kind of a plane. So it's actually very, very tough to generalize. Okay? So here, I will not even attempt to understand it geometrically. However, the notion of derivatives is still there. Why is that? And, and the idea is that you can actually use a derivative mechanism to actually approximate these functions. So you have basically two functions here. You have f1 xyz and f2 xyz, and you can actually consider, two rows of those partial derivatives. So you can say delta f1 to delta x, delta f1 to delta y, and delta f1 to delta z. What will be the first row here? The first row here will be, it will be basically 1, 1, 1. Okay, because delta f1 to delta x, those two guys are constant. So when you derive them, you get 0 and you get only the derivative here. Delta f1 to delta y, those two zeros, and you have only derivative here. And delta f1 to delta z, those two zeros, and you have derivative here. And the xy, you're getting, so when you derive with respect to x, you get yz. When you derive with respect to y, you get xz. And when you derive with respect to z, you get xy. Okay, now you can actually approximate before we talk about approximation. Now, let's say if you want to know what is the derivative at a certain point. So you say x equals, let's say, 2 at this point. So we said, let's say x equals 2, y equals 3, and z equals 5. What is the derivative at this point? Okay? So here it's not very interesting. You get 1, 1, 1. So you get 1, 1, 1. What's happening here? Y times z 2 times 5 is 10. X times z 3 times 5, y times z is 15. X times z is 10. And then the last but not least, x times y, 2 times 3 is 6. Okay? That's all. So the derivative at this point, will be a matrix. You see? It's a matrix. It has 3 columns and 2 rows. So it's a 2 by 3 matrix. Okay, so the derivative in this case will be 2 by 3 matrix. Where it's coming from? It's coming from because this guy is a vector and this guy is a vector. Geometrically, you can think about those two guys as defining a plane. Okay? As defining a plane. Note that if you take, and for example, this guy corresponds, to this plane, and the xyz corresponds. This vector defines a plane. Now, this is going to be basically a 3-dimensional plane, right? So before that, we had z equals to f1 of xy. And here we said that we are having delta f to delta x and delta f to delta y like this. Here we are actually having, 3 guys, right? X, Y, Z. Okay? So here we have a 2 by 3 matrix. Now how do you use this matrix in order to approximate the function? Is exactly the same idea. So let's start with a point. So we said that we are going to start with a point as before. So x equals 2, y equals 3, z equals 5. So we are going to have here, what is going to be the 2 points that correspond to this function? So it's going to be x plus y plus z. It is going to be 2 plus 3 plus 5, which is going to be 10. And here the point is going to be 2 times 3 times 5, which is going to be 13. Okay? So if 2 planes, the point is 10, 30. Now I'm going to move those vectors, let's say so delta x, I want to move by 0.5. Delta y, I want to move by 0.25. And delta z, I want to move by 0.25. So what kind of point I want to calculate now? So if x I'm moving by 0.5, I'm going to get 2 times 0.5 is going to be 1. Sorry. I'm adding to x 0.5, so I'm going to have 2 plus 0.5. So the x new is going to be 2.5. Here, x new, y new is 3.25. And here, z new is 5.25. Okay? What I want to do now, I want to calculate the function at this new point, 2.5, 3.75, and 5.25. So how do I do that? Well, what I want to do, I want to calculate it separately. So it's what I'm just going to do. I'm just going to multiply this matrix. Okay, I'm going to multiply by the delta vector. So I have delta x as going to be 0.5. Here I'm going to have 0.25, and here I'm going to have 0.25. And now each row will give me the new by how much I need to change the function in order to get to the new point. That's all there is to it. So when I'm looking on 1 plus times 0.5, I'm moving by half in the x vector, in the x direction. When I'm looking on 1 times 0.25, I'm looking by 0.25 in the y direction. When I'm looking on 1 times 0.25, I'm looking on this in the z direction for the first function, right? Because remember that f1, x plus delta x, y plus delta y, z plus delta z, minus f1 of x, y, z, we said the key formula is going to be that this is going to be delta f to delta x times delta x plus delta f times delta y plus delta f, plus delta f to delta z times delta z. And here I'm going to put f1. So it's delta f1, delta f1, delta f1. So when I'm taking this matrix, I'm multiplying by this times this corresponds to this this times this corresponds to this, and this times this corresponds to this. Okay? So overall, it's going to give me the total change of f1 minus f of x, y, z. So by how much I need to move, okay, my point here in order to get the new value. Okay? So here it's going to be 1 times 0.5 plus 1 times 0.25 plus 1 times 0.25. I'm going to get here 0.5 plus 0.25 plus 0.25. So here I'm going to get just 1. Is this clear why? Because it's this times this plus this times this plus this times this. I'm just multiplying matrices. Here, okay, we said that the value is going to be, so it's 1.5. So we have 1.5 times 0.5, so it's 0.75, plus 10 times 0.25, which is 2, plus 6 times 0.5, which is 1.5. So overall, you're going to get here 225 plus 2. You're going to get here 425. Okay, so when you multiply this by this, when you multiply this vector by the change, by the vector of the changes, when you multiply this matrix by the vector of the changes, you're going to get something of the form 1, 4, 25. Okay? Because you took a 2 by 3 matrix, you multiply by a vector, which is basically 3 by 1, and you get something like this. You get 2 times 1, 2 by 1. Okay? And what is this 1, 2, 4, 25 represents? It represents by how much I need to move my point, which I have here, in order to get the new approximate value in this case. So here I have, we said that it's going to be 2 plus 3, whatever it is, I think plus 5. So 2 plus 3 plus 5, we said it's going to be 10. So I need to take 10, and I need to add 1 to it. So I'm going to get 11. And here I'm getting, we said x, y, z. So we are going to get 2 times 3 times 5, I think. 2 times 3 times 5 is going to be 30. So here I'm going to have 30 plus 4, 25. So my new guy, my new approximate value is 11 for this point, for the two functions evaluated at this point, 2.5, 375, and 525 are evaluated at this new point. So it's going to be 11. And then here it's going to be 30 plus 4, 25 is 34 plus 25. Okay? So that's how the approximation works. So it's a pretty straightforward process. It just needs practice. Okay? The idea here is that when you have something like that, if you have when you have a function from Rn to Rm, you can think about this as basically being m one-dimensional function. So it's f1 x1 to xn, f2 to x1 to xn, fm to x1 to xn. Okay? And if you have something like that to derive, okay, you're going to get n by times n matrix. Okay? This matrix is called the Jacobian. Okay? So the partial derivative matrix for a mapping like that is called the Jacobian of the mapping, and in some sense a generalization of the tangent. And you can see why it is used. It is used to approximate the function. And now I'm going to show, and now I'm going to explain the application to, to machine learning and all that stuff. So when we talk about, when we talk about equations, when we talk about solving equations, we said that, in the one-dimensional case, we have the following algorithm. Let's say that we start with a guess. We start with an initial guess. X0 is our initial guess. And now we want to solve the in general, we want to solve the equation f of x equals 0. We start with the initial guess, f of x0, f of x0. Let's say we want to solve the equation, we want to find the square root of 2. How can we find the square root of 2? We can think about this as trying to solve the following equation. 1 plus x squared equals 2. That's an equation that we want to solve, right? So if we want to try and solve it, we start with a guess. Let's say x0 equals 0, or x0 equals 1. Doesn't matter. Okay. Now, how do we find the next point? We said that we want now to approximate this equation, f of x equals 0. We want to approximate with the equation f of x plus delta x equals 0. F of x 0 plus delta x equals 0. So we want to take our initial guess and move it so that it will be closer to 0. And then we said that we are now going to use our formula. So it's going to be f of x0 plus f prime of x times delta x, which is going to be 0. Okay, and now you solve this. and then you are, you put it on the other side. You said that delta x is just going to be, what is going to be delta x? So basically, in order to find the correct, quote unquote, the correct equation, the delta x is going to be here, basically minus f prime of x. So you basically move it to the other side. So it's going to be f of x0 divided by f prime of x0 minus. Okay? So now the new point that you have is going to be x0 minus f of x0, f of x0 divided by f prime of x0. Right? That's your new point, and this is called the Newton method. How is it going to reflect on this? How is it going to reflect in general case? Well, in a general case, what you are going to have basically a system of equations that you want to solve. So this is going to be now not necessarily, okay, one equation, but it's going to be multiple equations. For example, you have the following system. You want to find all the points such that x, y, z equals 0, and then you also want to find, for example, that x square y plus y square z plus z square y square equals 0, something like that, right? Let's say x square equals 0. You have a more complicated setup, not just linear equations. You have something like that. You have nonlinear equations. Now, why is it important in machine learning and all that? Because in machine learning, what you want to do, you start with a certain target, and you want to converge to the real target. How do you converge to a real target? Well, you have some sort of a learning algorithm. But what does it mean to have a learning algorithm? To have a learning algorithm on its most elementary level is to try to solve some equations like that. Because if you are here, it's an initial guess. You want to go to the real point. You want to have systems of equations like that that you want to know how to solve. How can you solve something like that? Okay. So the idea is exactly like you have here. So what you want to do, you start with your initial guess, which is, let's say, x0, y0, and z0. And now you are saying, okay, I have an initial guess, but it's not a good guess. So what I want to do is to approximate it. What would be my approximation? I need to find delta x, delta y, delta z, such that, for example, in this case, I'm going to get that f of 1, x plus delta x, y plus delta y, z plus delta z, and f of 2, x plus delta x, y plus delta y, z plus delta z will be equal to 0. In this case, what I want to say that I want basically something of this form. I want that x plus delta x plus y plus delta y plus z plus delta z will be closer to 0 than my initial guess, x0, y0, z0. And here what I want that x square, x0, y0 square plus y0 square, z0 square plus z0 square, x0 square would be the here, right? I mean something, not this, but sorry about that. So let me rewrite it again. It's going to be x0 square plus x0 plus delta x 0 plus delta x square plus times y plus delta y plus here I'm going to get y plus y0 delta y square times z plus delta z plus z plus delta z square times x plus delta x square equals 0. Okay, so I want to find something which is going to be closer to me. How do I find such delta x? Well, I'm going to use the derivative formula. So I know that in this case, I have something like that. I know that in this case, f of 1, let's say my vector f1, f2, fn, let's say fm, x0 plus delta x, y0 plus delta y, etc., etc., etc. Here it's x0 plus delta x, y0 plus delta y, etc., etc., etc. fm x0 plus delta x, y0 plus delta y, etc., etc., etc. I want this to be 0. I want this to be closer to 0. So what do I do here? I'm just using this guy. I will say that in this case, I'm going to replace the formula f of x0 in one-dimensional case what I'm going to do, I'm going to replace this guy with the following. This is going to be f of 1, x0, the vector f of 2, x0, f of mx, x0, plus, and now I'm going to take the Jacobian of my matrix, and I'm going to multiply by the difference. X0, Y0, Y0, plus delta x, plus delta y, etc. I'm going to take this guy and multiply it by delta x, delta y, etc., etc. And this, I will say, must be equal to 0. So what I'm going to do now, I'm going to solve these linear equations. Okay, and we know that the only way for us to kind of, when we have a solution is when this Jacobian is invertible, when this matrix is invertible. So now we are going to say that n equals m, so that we can deal with invertible matrices. Okay, and then what you are going to get, you are going basically to get delta x0, delta y0, blah, 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 delta something here equals your Jacobian times your vector that you started with here. F of 1, x0, f of m, f of n, x0. Okay? So now what you want to do, you will say, okay, I will take these x0s and I will add this, and this will be my new approximation. Do you see how it works? I'm going to replace, in this formula, this quotient, I'm going to replace with this expression. That's why it is useful. That's why it is the most important algorithm, in all the, well, it's one of the most important algorithms that we have. All, artificial intelligence actually starts from this observation. Actually starts by how do you solve this kind of nonlinear equations. Okay, so what you want to do now, you want to calculate this. Well, here it's not going to work because you have 3 by 2, but let's say that you had another equation, say xz plus z plus xy equals 0. Here you have a 3 by 3 matrix, you invert it, and then you kind of act on this vector, and you get the next step of your approximation. And the surprising thing is that this is a very powerful algorithm. You have hundreds of people and hundreds of papers that make a living out of trying to analyze when this algorithm is good, when it's bad. There is a lot of stuff which is going on here. Okay? Now, a last application to finance. If you have a bond, say you have a bond, okay? We said that the price of a bond is e to the minus yt. But what does it mean to be e to the minus yt? So we can say that it's yt times t. So if the curve is not constant, what we call the interest rate curve or the yield curve is not constant, something like that. Okay? Let's say the teeth is your 10-year. But what you want to do, you want to understand what is the dependency if you move the 9-year point. So So if you move the 9-year point, your 10-year point will move. Okay? You want to understand the dependency on this move. So in order to understand the dependency on this move, okay, or you want to calculate some sort of a duration for this move, what you want to do, you want to actually calculate 1 over p, delta p to delta y, but instead of getting a t here, you want to take delta y t small, where t might not be big T. Okay? So for example, if you say, okay, I want to approximate, I don't care about other points, I just care about a 10-year point. So if you want to calculate, so if you have a 10-year zero coupon bond, so you have something like that, and now you want to calculate the partial with respect to y10. You want to calculate the partial with respect to y10, it will be something like that. It will be 1 over p10 delta p 10 to delta y10. And here it is going to be minus t. Okay? So here, the dependency on the 10-year point actually coincides with the duration. Okay? If you have a different point, you may say, okay, maybe it doesn't depend, maybe it depends, we don't know. But if, let's say, you have a 9-year point, okay, what you want to do, you want to understand how a 10-year point will move and then to multiply by this minus t. Okay? But here, what is the difference between this and the previous calculation? In the previous calculation, when we said e to the minus yt equals p, okay, we didn't care what the yield point is at. We actually assume that the yield is parallel, that the yield is constant. Okay? When you are introducing something like that, when you're introducing curve slopes, okay, you cannot just say, okay, I will ignore the time of the yield curve, the interest for this interest, because maybe the 1-year and the 10-year interest are different, and when the 10-year interest will move, maybe the 1-year will not bulge. Okay? So here, and then if a 10-year moves and the 1-year doesn't bulge, then delta p e minus y10 times e minus y1 times 1, okay, with respect to 10 will be 0, for example. Okay, so you need to take the dependency not just on the yield curve but on the point of the yield curve. Okay, so I'm going so these partials that we have in finance, 1 over p delta p minus y over p delta yt, these are called partial durations. Partial durations, or they are also called key rate durations. And they are very, very important in risk, and we are going to talk about this during the course. Okay, so just to recap today, what we covered today was basically partial derivatives in general. What we are going to do next time, what I'm going to talk about next video, I'm going to talk about integration. I'm going first to talk about one-dimensional integration, then I'm going to talk about multi-dimensional integration. And integration in higher dimensions is a little bit tricky, so we're not going to dedicate too much time for that. But we have to understand that how this works in order for us to talk about, derivative, probabilities and probability distributions in n-dimensional space. Okay? So I'm going to end now, and thanks for listening.